Alrighty, 11 o'clock. We got a lot of content to get through here. Appreciate you guys sticking it out till Sunday. I know there's a lot of people leaving, but definitely appreciate you coming out. Show of hands real quick. Who has heard of SPARTA? Okay, about half. Okay, that's good. So you're going to learn a little bit about it, and then we're going to get into something more specific. So I'm going to go through the first few slides pretty quick because I want to get to the important content. This is my bio. I've done a lot of pen testing and different things related to security, a lot of NASA work, and more so recently spacecraft cybersecurity. All right, so SPARTA, what is it? I would assume everyone in here has heard of MITRE ATT&CK. It's been around 12 years. So when we started looking at space system cybersecurity, we were like, okay, we need to be able to a method to communicate TTPs for space systems. So how do we do that? And we saw what MITRE had done, and I'm an aerospace, I'm an FFRDC, MITRE is an FFRDC. So we said, hey, we're gonna kind of use your template and build the same thing, but for the space vehicle and the link segment. So we did that. October 2022, we published MITRE ATT&CK, or we published based on MITRE ATT&CK SPARTA. And really what it is kind of the soup to nuts threat modeling thing for space systems. So it has everything from EW, ASATs into cyber. It's really heavy on the cyber side, but we do have some of the kinetic things in there. And one of the key aspects of SPARTA, what we were trying to accomplish is basically take threat intelligence or things that we would consider threats, transition them into techniques. And then the whole point that we're doing that, so this isn't, so like a thing like MITRE ATT&CK typically is mostly focused on documenting TTPs that have happened and actually trying to like retroactively document attackers' methods. We do the same, but we're also trying to project and theorize what attackers could do in the realm of space systems, because we don't have a large data set of attacks to pull from. You know, there's a handful plus, maybe a dozen to pull from. So what we're trying to do is communicate the threat levels and then decompose those into countermeasures and requirements. So the whole point of SPARTA is really to drive the blue aspect. So red informed blue, threat informed information is what we're trying to accomplish. So within the tool set, we have all the techniques, all the ways to mitigate or help mitigate. And then we even have it all the way down to requirements, like shall statements for people that do system engineering. Spacecraft people do obviously system engineering. So that's what we're doing. So why are we here today? So we use that same process that we built from the beginning of SPARTA, which is basically get down to the lowest level that we can get to for mitigation. And we did a process for indicators of behavior. So I would presume that most people in here have heard of IOCs. That's a term that's pretty common in the cyber world. You know, those are the file hashes, domain names, things like that for malware. So a little, I guess, a less known thing within the STIX framework and the standard put out by OASIS is called indicators of behavior. It's only a few years old. So we adopted that methodology because what we're trying to do is one of the countermeasures that we feel like is going to be most beneficial in the future is intrusion detection type capabilities on space vehicles. So if you're really new to kind of the space realm, there are not a lot of detect type capabilities built into spacecraft, if you're not aware of that. What we do have typically is what's called FMS or fault management. There's, FMICA, fault management exercises that go through all the faults, but they usually don't consider security as a part of one of those fault methods. So they typically think about randomized faults, like things environmental. And security is really kind of the same thing as a fault, except it's invoked by some actor, insider or whatever. So what we're trying to do is use the same methodology and decompose as many ways that we can think of to what an attack would look like on the spacecraft. So we've already built kind of the threat model of all the ways to attack the system. And then we did a research study that said, hey, is intrusion detection even a thing on a spacecraft? Can it work? And that turned out to be, yes, it can. And then the next question was, well, what do you look for? Because that was where people were struggling is, okay, we buy in that we maybe should be looking for cyber intrusion on a spacecraft, but I don't even know what to look for. So this is where this came in. So what we did in April of this year, through some funding with Department of Homeland Security, S&T, Science Technology Directorate, we basically tried to decompose as many SPARTA techniques that we had into indicators of behavior so that we can use it for detection engineering. Now, there's a blog post that goes into much more detail that you can go read on Medium that's about this. So what we were trying to do basically is identify some of those behavioral patterns. So, IOCs are more the known knowns. So like I said, file hashes, IP addresses, domain names, that kind of thing. IoBs are more in the probabilistic area, behavioral based, and they're a little higher level abstraction. And that's what we needed for what we're trying to accomplish. So on SPARTA's website, there's under related work, there's now a thing called indicators of behavior. Also, if you click on any individual technique in SPARTA, what you'll see is a tab for indicators of behavior along with countermeasures, requirements, and all that type of stuff. So it took us, 6 months or so to come up with these, and we feel like it's going to allow developers to build detection capability on the spacecraft. And we did a little kind of a case study applying that theory using these. Our first iteration in April was about 200 so far. So how do we do this? It wasn't just theory, like, hey, let's think up ideas of what an attack would look like. We actually had to attack varying levels of space systems. So we attacked digital twins. We did attacks on flatsats, and then we also have, I have 10 years of pen testing experience in space systems, as well as a lot of test and evaluation while I was at NASA. So basically, we kind of had a good baseline of understanding of what this would actually look like. So we're kind of red teaming it, if you will, to drive what those defenses look like and what those behaviors would look like. And how do we, right now SPARTA has 215 or so techniques. And the question was, well, we're not going to derive an indicator for every single one of those in the first release. So how did we actually get to our first baseline set? We basically used the most dangerous, impactful, likely techniques that exist in SPARTA and derive the indicators from that. So we know that once the detections that you're going to have to do is going to have to account for a lot of different aspects. It's not just security logs, it's telemetry logs, it's bus traffic, and all sorts of things on the spacecraft. It's a little bit different than in the terrestrial world, because there's a lot of subsystems, and a lot of the attacks are going to show up in like the subsystem behavior on the spacecraft, and not necessarily what you would typically see like in an event log on a traditional system. So once one of the things we realized is it was good to do a generic indicator of behavior, because it's going to provide people enough information that they can then derive based on their implementation of the spacecraft. And what we did was we used STIX as the method of communication. So basically, STIX, if you're not familiar, it's a cyber threat intelligence standard, and we've used as much of that as we could. And what we realized also is STIX is very stringent on the observables that are in the standard. And what we realized is like a lot of the things that would be in a space vehicle don't show up in the STIX standard. So there's a whole effort with OASIS and the Space ISAC to extend the STIX standard into space, have space observables in the standard moving forward. And so we have validated a lot of these in environments. So we're going to talk about these. So I'm going to really jump through these really, really quickly, because I'm not going to talk about each individual one, because I want to get to some of the videos. So basically, we came up with 200 indicators, and we categorized them in kind of 10 categories, because it's kind of how it made sense to us, and that's how they worked. And it kind of makes sense, because if we derived everything from the most risky SPARTA techniques, these categories kind of make sense. So the first group was related to commanding, unauthorized and anomalous commanding. The next one was related to crypto usage and crypto key manipulation and encryption bypass. Then it moves into like network exploitation and communication security. Then you get into signals, RF integrity and authentication. And then you get into timing and GNSS, GPS. And then you start getting into the little more complex attacks. So attacks on the memory and resource utilization within the spacecraft. Then you start talking about watchdogs and registers. and then software integrity and unauthorized updates like patches and implants, and then sensor manipulation and resource exhaustion, and then you get into data integrity. So it kind of makes sense if you think about if you work in this field, it should make sense to you. You're starting in the commanding and the signaling and the RF side, then you move into the memory and the watchdogs and the registers, and then kind of software integrity and data integrity and sensor manipulation. So it's easier to do the top ones, harder to do the lower ones. It's kind of what you should think about. So what does it look like? Like in the website, basically, anytime you click on one of these, you're going to see what it is, the description of it, the sticks pattern, and then you're going to see all the correlated techniques. So what does that mean? That means we feel like if you implement that specific SPARTA technique, this sticks expression should help you detect, the attack. So we wanted to prove that this was the case. So how do we do that? We basically set up experiments and attack the system using. We had to build an IDS first, attack the system, and then see if it flags. So we wanted to know, could a developer who did not create these sticks patterns and indicators build detections based on them? And actually, the one who did it's in the room, Randy Tenney, she's back there. You might have seen her at Aerospace Village. But she took what we wrote as the indicators and actually turned them into detections on a spacecraft and built an IDS for a spacecraft. So one of the experiments we did, if you were in the Aerospace Village, you've probably seen NOS Cubed quite a few times at this point. And it's a digital twin software built by NASA, open source, free. Definitely encourage you to use that if you've never actually used any type of ground to space simulation. That was actually made by myself and Randy, both are from West Virginia, and we worked at the NASA facility who manages and builds this thing. I even contributed early on development on NOS Cubed actually when I was working there, and then I moved into security. So then we had to build a space cop. We came up with that name. We actually had the first name we came up with was Starshield. And then, unfortunately, Elon Musk and SpaceX stole that because we didn't trademark it, and now they're making billions of dollars selling it to the DoD. But, it's what it is. So we came up with a different name, and this is what we're going to go with. So what we did was basically write an IDS called Space Cop, and we took a subset of the 200 and made 300, took about 30 of the indicators and wrote an IDS based on that. And one of the common things we get when people talk about, well, if you're going to add more capability or add more software to the spacecraft, what's the impact on the utilization? So you can see it's pretty negligible. At least this first rev of it, it really is negligible on what you actually would impact the system. So there's some links. There's a public thing about Space Cop, and there's NOS Cubed as well. So one of the experiments we did is a very, very basic one. So, I don't mean to necessarily wow you with how complex this attack is, but if you know how spacecraft operate, timing is extremely important. Just like, GPS timing and everything operates on time clocks. And so one of the attacks that's pretty common is to try to spoof the time so that you can make the spacecraft do things that it shouldn't do. So what we did was basically, built the detection, and then we just, send a command to change the time. So in the signals world, right, that would be some sort of time spoofing signal coming from an RF link. But in the simulation, we just told the time to jump to a specific number to see if the detection fires, because the same thing would happen if it was an actual signal. So it's pretty basic, right? Basically what you're going to see is a command going from the ground station to flip the time above the delta that we had. So this is, and then what you're going to see is obviously on the downlink in the telemetry, you're going to see some sort of indicator. Pretty basic. So what you notice though in the real world, in the ground to space, right? If that was a real attack, you wouldn't even know it happened until the telemetry came down on the downlink. So that could be, that time spoof signal could have been sent, and then you wouldn't even know till 15 minutes later, because you wouldn't know until the telemetry is downlinked that something happened. So we'll get into kind of that. in a minute. So we said, okay, it worked once. How does it scale? Can you take all these SPARTA indicators and make them into something real? So we already tested. Can we build take 30 of the 200 and implement them in an IDS, and attack it and see if it detects? And that was successful. But then we wondered, hey, does it actually scale to real missions, a real satellite with mission-specific data? So since the indicators are very generic, they have to be mapped to telemetry, command logs, and onboard activity. So that's a challenge. And if you're not familiar with space vehicles, there's tens of thousands of mnemonics and telemetry items on a spacecraft. So it'd be very time-consuming to go through each individual mnemonic and say, okay, is this an indicator if this is a certain value and goes above a certain threshold of a malicious action? So that's what we wanted to test out that theory. So we knew we had to translate it. So we were saying, what do we want to answer? Are the IoBs specific enough that they can tie to mission data and they can drive detections? Can you map those to existing data, and can you translate? Can you do that at scale? What's the engineering lift needed to be able to accomplish that? So basically what we did was we worked with a group with a real mission, and we said, hey, can you basically translate these indicators into telemetry items on your system? So what we found was basically, yes, they can, and it actually was automated. They did it, instead of doing it manually, they automated it using some AI and machine learning type of capabilities. So they took all 200 of our indicators and matched them up to roughly 90,000 different mnemonics that they had, which translates to lots of different types of combinations. So that was pretty interesting to see that could that actually be done in an autonomous fashion, because we know that's one of the pushbacks we're going to get from industry and others, is saying, well, it's just going to take me forever to map out these 200 things to all the telemetry items I have. And so we already have proven that can happen. So that's good. We did that with our application called DARS. It's an aerospace developed intrusion detection system on the ground that monitors for, it was monitoring mainly for signal interference and GPS. But now it's monitoring for cyber intrusion, because they've added this capability. So we said, okay, we've tested it out. We can translate to missions. We've done some basic time attack. The question was, do these indicators actually help with more advanced attacks like onboard malware and onboard persistent threats? So we want to say, okay, if you put malware on a vehicle or compromise the boot code or deploy a rogue application, will these indicators of behavior, if you decompose them properly, detect that type of an attack? So we did. So basically what we had is if you're familiar with CFS and NASA's core flight system, they work in something called applications. So if you've ever seen their architecture diagrams, they're little bubbles, and then there's a bus that communicates, that they communicate on. So what we did, actually I didn't do it, Randy did it, so I'm not going to take credit for that, but she wrote a rogue CFS app called Blackout that basically acts like some sort of implant on the spacecraft. So we uploaded it. So what were we trying to do? We were trying to simulate kind of a malicious update or some sort of supply chain inject, because it could be embedded in an existing app, or it could be an app by itself. But we wanted to kind of test out this theory of, hey, if someone was able to upload some rogue application and start executing rogue attacks, could you detect it? So how do we test this out? We used our pen test tool that we have called Space Invader. It's pretty good name, if you say so. So it's SPARTA Cyber Exploiter Invader. You got to come up with acronyms if you work in the government. So that's what we did. If you're familiar with man-in-the-middle and ground systems and rogue ground systems and things like that, this is basically acts as a man-in-the-middle tool and a rogue ground station that you can communicate. It can intercept data, modify data, spoof data, jam, all sorts of interesting things. Then it can also, it's been coded to communicate with Blackout, the rogue application as well. And Space Invader does all sorts of different things. So if you're in the government space and want to work with us on it, please contact us. We can help out with that. All right. So the question was, can we detect this? Obviously, you would imagine this is going to be successful, or we wouldn't be putting this on the screen here in front of everyone. But basically, the way it works is we've already uploaded the app. Well, we're actually uploading the app now, and so this is the rogue ground station, the tool. So we're essentially uploading the attack and the app up there. And because the way some of the indicators were, we had certain areas where, in a spacecraft is very deterministic. So it's very easy to build detections, if you will. So as soon as the file touches disk in this area, it triggers, because there should never be things hitting this location. And then essentially now you're going to send a command and execute ransomware on the spacecraft. You'll see like it's executing and then encrypting the files. And then you'll see all these detections fire here in a second. So you see all these different commands that are getting executed by the ransomware, and it flags. So, okay, fine. You detected some basic things that were going on, rogue malware and things like that. So that's part of the story, and that the indicators are extremely important from that perspective. But there's also something else that we need to talk about, is if that was a real attack and then all you saw was in the telemetry on the downlink those messages, you'd be in a world of hurt, because you actually don't have the control loop is so low, you don't really have time to take any action. So detection doesn't equal mitigation. So you can detect it, but what do you do about it? So I guess it's kind of good to maybe know after the fact that something happened, but in the space world, you don't really have time to react, and you need to actually take action. So that's what we need to really think about as an industry. If you're in this area and you're doing research, you can imagine if you've done any research and attacked a spacecraft, there's really not a lot of time to get the data down and then analyze it, forensics, and then command it to do something different. So what we got to do is really think about autonomous response. Spacecraft are autonomous anyway. If you're familiar with it, basically they take care of themselves. So they have to do the same thing for security purposes in the future. So detection's not mitigation, and we need to think through that. We got to have autonomous action, and this isn't new. We Aerospace Corp have been saying this for a long time. Automated response integration with fault management is critical. That's kind of where we need to go. So that's one of the reasons why we wanted to build these indicators, is to help with the detection so the response can actually happen. So we need to think about cyber in that fault management way. So like this goes back to 6 years ago. There was a paper that I wrote in 2019 that was talking about this, and we're finally getting people to kind of realize that this is important. So there's all sorts of quotes in there. If you haven't read it, you should go read it. Basically, fault management, intrusion detection, and all these things are extremely important, and we need to think about that moving forward as we design these systems. So now we have the threat model, we have SPARTA, we have all the techniques. Now we have at least a good subset of indicators to build intrusion detection against, and we're going to expand those moving forward. So basically what we're trying to do is, can we build IoBs? Can we implement those IoBs in an IDS? Can we attack the spacecraft, get the detections? Yes. And then we realized, because we wrote all sorts of different attacks, many of them the vehicle was non-recoverable after, and we actually we've done that in flat sats and in orbit, a bunch of different attacks, and we realized quickly that you have to basically respond as soon as the event is detected, if it's one of the more dangerous indicators and detections. So I would ask if you've already used SPARTA, scan that QR code, go to we have a survey that we're wanting some feedback for new features and things like that. So please go there. On the resources page on our website, there's all sorts of links to different briefings, trainings, media stories, and all sorts of things out there. So go forth, And these slides will be posted on the media server, so you have all these links because they're hyperlinks. So taking pictures aren't really going to help you too much. Yep, but that's it. If you, I got some stickers from SPARTA stickers if you want any. I have some of these cards with the survey link. If you want to do that, appreciate you guys coming out. I don't know if there's a minute or two for questions. Looks like it's 11:24, so we got about 5 minutes that they're going to clear out. But I'll be around if anyone has any questions. Love to have any feedback you have on what we're doing at Aerospace Corp. Appreciate it.